let's do some live coding. I want to start off with this physics demo that's pretty awesome and people love it. And I have two versions. Number one, string right here attached to the top and the bottom of this 1 kilogram mass. Let me just go ahead and play it. I've already recorded it. So I'm going to pull down on the bottom string, and which string is going to break? Break. Top string broke. Okay, next demo. It's the same thing. But now I'm going to pull down on the bottom string again. So just a narration here. I'm using this little PVC pipe just so I can get a grip on the string. And break. Bottom string broke. So it's a great demo because you can do it really easily. If you pull slowly, the top string breaks. If you pull really fast, the bottom string breaks. So you can make anyone be right or wrong no matter whatever you want, and it's a fun thing. So why does the bottom string break? You could say, oh well, because the object has inertia, which is true. If you want to make that object accelerate, it's going to have to have a large force. Let me show you number one. Just a simple free body diagram with some forces equation, and we can think about what's happening here. And then I want to model this in Python so that we can see that which string breaks depending on how fast we build it. That's what I wanted to do. Live coding modeling of that situation. First, go into the paper. Okay, so if I have a block right there, and I have the downward gravitational force, mg, it's a vector, and then I have the tension, I guess I should draw it big, T1, and then I have a pull down on a string, T2. And I poorly picked all these things. So now if I'm pulling it very slow, then the acceleration is 0. So then F net in the y direction is going to be equal to the tension T1 minus mg minus T2. So these are minus because it's in the y direction. And let's say I pull very slowly so the acceleration is 0 or very, very close to it. Then this is true. Now I can control the value for T2. I can pull on this, because there's a string and my hand is right here. That's a finger. Well, I'm pushing, but I'm pulling on it down so I can pick whatever value I want that to be. So I can solve for T1. So T1 is mg plus T2. So no matter what value I pick for T2, T1's going to be greater. So let's say there's some T max. Let's say this is 1 kilogram. So T max is 100 newtons, right? Because this would be 10 newtons, right? 10 newtons? The mass would be 10 times 1, 10 newtons. So if the tension's over 100 newtons, the string breaks. Well, T1's going to break first, right? Because there's no way T2 gets there first. But now let's assume that I pull really fast and try to make the block accelerate down with some negative value, negative a in the y direction. I can rewrite the equation. I get T1 minus mg minus T2 equals minus ma, where that's the acceleration. Now if I solve for T1, I get T1 equals T2 plus mg minus ma. So if the acceleration's large enough, larger than the acceleration due to the g value, then t is going to be less than T1, right? And if that's the case, then T2 string can have a higher magnitude than T1. As I keep increasing T2, it can be higher than T1, and the bottom string can break. Okay, but you never really understand something until you model it. So let's model this. Of course, we're going to use Web v Python. And what I'm going to do is start off with my box, which is going to be a ball. And I have the downward gravitational force. That's cool, mg. But then how do I model the tension from a string? Well, the answer is to replace the string with the spring. So I like to say the string becomes a spring. It's just one letter difference, right? So it should be easy to do. The nice thing about a spring is that I can calculate the exact force. I don't know the force of a string, right? But the string does stretch. It does exert a force. It depends on the stretch. It is a spring. A string is a spring. It just has a really high spring constant. So let's do this. I'm going to say this has an unstretched length L0. I'm going to calculate the vector. Let's say, which way should I go to this? This vector I'll call L. if I do that, I can write the force on the mass down here as F, we'll call it F1 because it's a tension 1. I'll call it T. T1 is going to be equal to K, the spring constant, times, let's say, L minus the magnitude, L0 minus the magnitude of L, times L hat. So L is a scalar value. This is a vector. And so I can't subtract a vector and a scalar, so I need to take the magnitude of that first. But then I'm left with a scalar quantity, and I need it back as a vector because I'm going to use the momentum principle. So I need to multiply it by this unit vector L hat. And so let's just check and make sure the direction's right, because I always get the direction wrong. I want to find the force on this. So let's say I stretch it down, I pull it down more than the natural length, then the force should be up. So if that's true, then this is going to be greater than that, so this is a negative number, but L hat's down. So I get negative L hat, so it does point up. So that's correct. And that's that. So let's just build a model with a single mass and our force on there. And I need to pick some values. So let's say the mass is, I'm going to actually pick 2 kilograms. I'm going to pick K is 1,000 newtons per meter. I want it really stiff, right? Because I want a stiff spring. And then I'm going to pick the unstretched length is 0.7. I just picked that. I don't know why. So let's build this and let it run. Now, I'm going to go ahead and say also, if you haven't done a numerical calculation before, the key is delta T 0.001 seconds, which is small. So if I do that, I can calculate the net force on the mass. It's just going to be mg plus T1, whatever that is. I can calculate that. And then I can use that net force and assume it's constant with the momentum principle. F net as delta P over delta T. This gives me P2, P1 plus F net delta T. So P1 is momentum at the beginning of the time interval, P2 is at the end. Then I can use the definition of average velocity, V average as P over M, delta R over delta T, where that's the position. And I can solve for the updated position, R2, R1 plus P over M delta T. So calculate the force, update the momentum, update the position, and if I change the position, it's going to change my force, right? Because I'm going to change these values over here. So we got a bunch of stuff to do. I'm going to add the bottom string in just a second, but I just want one string on there by itself. So let's do that. Switching to Python. Okay, that's not Python. Using WebVPython, as always, let's just get started. G equals vector 0, negative 9.8, 0, L0 equals 0.7, K equals 1,000. What else did I have? Let's just make the mass. I'm going to put it at the origin. So let's call that M1. I don't know why I'm using 1. It's a sphere. Position is the vector 0, 0, 0. Radius is going to be equal to, what's a good value? I want to pick a good value. L over 10. L0 over 10. I'm just going to use it in terms, I like to do it in terms of L0, just in case I need to change the scale. And then let's make it yellow. Now let's give it a mass. M1.m equals 2. What else do I need? M1.p equals vector 0, 0, 0. That's this momentum. I need to update the momentum, so I need a momentum. Now let's put the spring. So I'm going to put like a top point up there too. Let's call that T1. It's the top point that the spring's attached to. It's a sphere. Its position is going to be equal to vector 0, L0, 0, right? So I'm going to move up L0. And then its radius is much smaller, so let's say L0 over 40, and I don't care what color it is. Now I'm going to add my spring, which is just going to be a cylinder. I'll call that TS1 for string 1. It's a cylinder Position is going to be t1.pos, right? So a cylinder has a vector point for the start and then a vector showing where the end is, and that's called axis. So the axis is going to go from t1 POS to m1. So axis equals final m1.pos minus the initial t1.pos. And then I have to give it a radius. Radius equals L0 divided by 60. Again, I just picked something. Let's just see what that looks like. Looks like nothing. Oh, there you go. So there you go. There's my little rotate around if you want to. Okay, looks good. Okay, I think we're ready to go ahead and calculate stuff. So I can say t equals 0, dt equals 0.01. I want a short time interval. And let's run it for a second while t is less than 1. Rate, let's run it in real time. Who really cares? Number 1, I need to calculate the tension in that string, right? So to do that, I need that vector L. I'm going to call it L1, right? Because I'm going to have 2 strings. So L1 is, it's the vector from T1 to M1. So it's M1.POS minus T1.POS. So that is a vector. Okay. Now I can calculate the tension. T1 is going to be K times L0 minus mag L1 times norm L1. So remember in WebVPython, mag is a built-in function to give you the magnitude of a vector. Norm is a built-in function to give you the unit vector in the direction of that vector. Now I can calculate the net force on the mass. I've been doing this, m1.f, associating the net force as a property of that object. Just makes it a little bit easier. It's going to be m1.m times g plus t1 plus fnet is sum, right? Yes, some of these may be in the negative y direction, but that's still a sum. We've already taken into account the negatives. Now I can use that to update the momentum, m1.p, m1.p plus m1.f times dt. Now I can update the position, m1.pos, m1.pos plus m1.p times dt divided by m1.m. Now I need to update that string, right? Because if the mass moves down, I need to extend the string. I don't need to move the position because that top position is not going to move. So that's just ts1.axis equals m1.pos minus t1.pos. Now I need to update time. Let's run it and see how much damage we did. I didn't even save it yet. That's living dangerously. Okay. It's just a mass oscillating on a spring. It's exactly what we want. Now, I don't want my mass oscillating. I want it to start at rest. So I could calculate the equilibrium position, but I don't care. Let's save this. I'm going to do a trick. Mass, pull, string, down. I don't even know what that means, but I did save it. So let's add a drag coefficient to that. And then, so what's going to happen is the mass is going to have a drag and it's going to eventually settle where the velocity is 0 and there's no drag, and then that's my position, and then I'll just print that out. I know it's cheating, but I don't really care. So let's call that C equals 5. It's just a drag coefficient. Down here for the net force, I'm just going to say T1 and then minus, this one is minus, C times m1.p. So whatever the momentum is, I don't care about the velocity, momentum, multiply by that value C and then put it in the opposite direction. So it will be a drag force. And let's run this for, let's say, 4 seconds, just to make sure it runs long enough. And then I need to print the final position, m1.pos, because I need that value. Okay, let's run this and see what happens. So you see, it's slowing down because there's always that backwards pushing force that makes it stop. And there's my final position. I'm going to copy that and then go up here and put that as my initial position for the mass. And now I'm going to run it again. I'm going to put this at time 0, so I have no drag. And now it just sits there. Okay, so now I have the mass starting at equilibrium. Okay, now the next thing I'm going to do is add another spring below it, and I'm going to put a point down at the bottom, and that point I can move with some velocity, and that's going to be the pulling speed, right? And then we can see what happens. So let's just make another thing here. T2 is the bottom one. It's a sphere. Position is going to be equal to the mass, whatever that is, m1.pos minus vector 0, L0, 0. So it'd be a length L0 below it. So the two strings are different lengths originally, but that's fine. But other than that, it should be just like T1. It has the same radius, L0 over 40. Now I need another string. I'm going to call that, surprisingly, TS2. It's also a cylinder. This position is going to be m1.pos, right? I'm going to start at I'm going to go down, m1.pos, and then the axis is going to be equal to t2.pos minus m1.pos, and then the radius is same, L0 over 60. Now let's give a velocity, v pole, equals, let's put it slow, 0.1. And so I'm going to give this t2.v as a velocity vector, because I don't care about the mass. There's no forces on it. I'm constraining it to move with that velocity. I don't need to calculate the forces on it. It's just going to be v pole times vector 0, negative 1, 0. So I'm pulling it down. Okay. Now I need to calculate L. Let's change this to some short, 0.3. I don't want it to run very long. I need to calculate L2. It's going to be the vector pointing down, right? So it's going to be t2.pos minus m1.pos. And then I can calculate the force, T2. It's going to be K. Should it be positive or negative? It should be negative. Negative K, because I want it to go up. K times L0 minus mag L2. L2 times norm L2. So the force on this one, I just need to add in. I'm going to leave that drag force in there just in case I want to add it later. T2, that's the total force. I have gravity, T1, T2, and then that drag force, but C is 0, so that's fine. Then I update the position, the momentum, update the position. I need to now update the position of the bottom mass. So T2.pos equals T2.pos plus T2.v times dt, so it's going to move. I need to update the bottom spring. So I update the top spring. The bottom spring, I need to change both its position, because the mass moves, and the axis. So TS2.pos is going to be equal to m1.pos, and then TS2.axis equals T2.pos minus m1.pos. Will it run? Let's see. Okay, it seems like it's working. What I want to do now is to plot the tension in the top and the bottom string as a function of time, and then I can see how those two values compare. So let's make a graph. G1 equals graph. Title equals string pull. Demo. It's a demo. X title equals T in seconds. Y title equals tension in newtons. No, it's capital N. And then I'm going to put width equals 400, height equals 200. Otherwise, it doesn't show very well. And then I need to have the two things to plot. F1 equals G curve. Color equals color.blue. Label equals top. F2 equals G curve. Color equals color.blue. No, red. Label equals bottom. Then that makes sense? So then down here, I'm going to plot the magnitudes of those two tensions. F1 dot plot T mag T1. I can't plot T1, it's a vector. I have to plot the magnitude. F2 dot plot T mag T2. Okay, let's run this. I'm only running for 3 seconds, and that's fine. Okay, so this looks like it's working. I'm pulling very slowly. There is some oscillation in there. That's fine. But this string has a greater force than that. How much? You'll notice that on average, it's about 20 newtons greater because the mass is 2 kilograms, G's 10. So that's what the difference between those two is. Looks great. Okay, let's run it for longer. Let's run it for 0.8 seconds. And you see that I have to pick when do the strings break. So let's do this. When do the strings break? I'm going to make a maximum tension, T max equals 100. I'm going to make a variable called go. Go equals true. And then this I'll say while go. And then this will keep running. And then down here, what I'm going to do is just to say if the magnitude of T1 is greater than T max, then print top string breaks. And I want to put go equals false, so the thing will stop. And then I want to do the same thing for the bottom string, not that. Let's just copy this. And that's wrong. T2, then the bottom string breaks. And then I just because I get scared, if the time is greater than 5 seconds, go equals false. So I'll stop it. I'm always afraid of putting in infinite loops because infinite loops scare me, especially with WebVPython, because sometimes you have to like destroy everything. Let's run it. Okay, so right there, the top string breaks just like we expected. Now, let's increase the velocity to, let's say, 3 meters per second and see what happens. Vpol 3. Run. Okay. It was pretty fast, but the bottom string broke. So here you can see that I'm increasing the tension in the bottom string because I'm moving that really fast. So that bottom string is stretching and increasing the force. The top string is not as great of a force because that mass is accelerating. So that mass has to accelerate, and the only way the top string increases in tension is when the mass moves, right, to stretch it. But in order to do that, it has to accelerate. In order to do that, you have to have a large acceleration on the string. So the top string broke at 100 newtons right there. Let's just try 2 meters per second. And I already did this before. So you'll notice here that there is a tension right there. Here they both break at almost the same time, right? It's possible that you can pull where they both reach the same maximum tension at the same time. And again, the time and when it breaks and which one breaks depends on the value of the mass, the spring constants, and all that stuff. But it's just a fun thing to do. If we can model this in Python, if we can model that physics demo in Python, then we can really understand it, and that's what makes things so much fun. Link to the code down below. Hope you had a good time. This was pretty fun to me, and I'll talk to you later.